Hey here, so now that we've started Unit 2, we're going to move on to Unit 3 and we are starting with the chemical industry. Okay, now this is my favourite topic, absolutely love the chemical industry, so let's make a start. Now first things first, the chemical industry includes a lot of things, so products from shampoo to concrete, okay, from paints to pharmaceuticals are produced by industry. Okay, so basically every single product you can think of, shampoo to concrete, paints to pharmaceuticals, pretty much everything are produced by industry. Okay, so chemical industry and just before we move on, that's where chemistry comes from. It's a combination of chemical and industry. Yeah, the chemistry. Yeah, chemical industry. So chemical industry is all about maximising profit and minimising the impact on the environment. Okay, the impact on the environment. So all that means is that they are producing no to little pollution. Okay, no to little pollution is produced. So we're going to highlight those 2 points. Okay, so it's all about maximising profit. Yeah, chemists, we're greedy, we want to make as much money as possible. Yeah, and why would you not? Why would you create a business if you weren't making money? So maximising profit, but at the same time, we need to be careful that we're minimising the impact on the environment. Yeah, we're greedy, but we care. We care. So, what you need to talk about, there's a couple of new terms. We're going to look at what a raw material means and what something called a feedstock means. So a raw material is a basic substance, okay? So it's a basic substance used to make other substances, okay? So a raw material, it's the most basic substance. You can't break it down really any further. So basic substance used to make other substances. So examples of that, and you'll know all of these. So fossil fuels are raw materials, water, yeah, air. If you think back to Nat 5, metal ores, okay, minerals as well, etc. Okay, so fossil fuels, water, air, metal ores, minerals, all examples of raw material. Okay, and as I said, the next term you need to know is feedstock. Right, now a feedstock is a reactant from which other chemicals can be extracted or synthesized from. Okay, so a feedstock is a reactant from which other chemicals can be extracted or synthesized from. So basically, feedstocks are made from raw materials, are made from raw materials. So we take our raw materials, we react them how we want, and then we create our feedstocks, which can then be used further to create the product that we want. Okay? Right, so I'm going to highlight those two because you do need to know them. You need to know, you can get asked what is meant by raw material, what is meant by feedstock. Quite a common question. Okay, you need to know them. You need to know them. Right, now, going to start looking at the sort of details of a chemical industry. So when developing a chemical industry, chemists, yeah, you, me, chemists, when developing a chemical industry, chemists must consider 7, yeah, not 2, not 3, 7 design principles. Okay, so every time we're starting up a new chemical industry, we must consider these 7 design principles. So I'm going to talk you through them. Now, this is, chemical industry is quite a short topic. Okay. Oops. But there's a lot to it because there are 7 design principles and you need to know them. Yeah, but the good thing is that the majority of them, in fact, pretty much all of them, actually, they make sense. Yeah, they do, they make sense. So I'm going to bullet point them. I'm going to say 3 in 1 bullet point, no, okay, because there's no point writing it out 3 times, you'll know what I mean. So the first design principle, we need to consider the availability, the sustainability, and the cost of feedstocks. Okay, so remember, feedstock is where our other chemicals can be extracted from or synthesized from. So that's our first design, well, our first 3 design principles. So the availability, the sustainability, and the cost of feedstocks. Now, remember, if we are creating, say, I don't know, shampoos, yeah, soaps even, say we're creating soaps. Now, obviously we need sodium hydroxide in order to break down a fat in an oil, but let's say we don't have any sodium hydroxide where we're building our chemical industry, then there's no point because we've got no availability of the sodium hydroxide. Yeah, let's say we do have some sodium hydroxide, but eventually it will run out. What's the point? Okay, so we need to be able to sustain the feedstock. And then finally, the cost. Yeah, if we're building a chemical industry and the cost of sodium hydroxide far outweighs the profit we'll make, then again, what's the point? So we need to consider these 3 things. Now the next one we want to consider is opportunities for recycling. Yeah, so we could recycle unreacted gases. Okay, very much like in the Haber process. I don't know if you can remember it from National 5 when we're making ammonia. We get unreacted hydrogen and nitrogen. So instead of just getting rid of it, we just put it back in. Yeah, so we recycle unreacted gases. So that's the third one. That's the 4th one. Okay, now the 5th one are our energy requirements. Yeah, energy requirements. So again, that's all to do with cost, energy requirements. If it takes too much, if it costs too much money in order to heat the reaction to its appropriate temperature, then again, what's the point? Okay. Now our 6th one is our marketability of byproducts. And what we mean by that, if you think about, go back to soaps, when we were making soaps, we use sodium hydroxide in an alkaline hydrolysis reaction of fats and oils to get free sodium salts plus glycerol. Yeah, now the sodium salts are our soap, but the glycerol we don't need, but it's good because we can sell the glycerol and make money. Yeah, so it's important that any byproducts that we're making, we could sell and make more money, because again, that's what the chemical industry is all about. It's all about making money. And then finally, the last one, okay, so marketability of byproducts was number 6, and then the last one is your product yield. Okay, now product yield is all about how much product we're getting and how much sort of well, I'll explain it later. So say atom economy. Atom economy and percentage yield. Now percentage yield we've already done, okay? So that's how much, like when we react something, what percentage of the reactants are getting converted into products. We're going to look at a new term, atom economy. Okay, so percentage yield, atom economy kind of go hand in hand, but we'll talk about that later. Now, as I said, you do need to know these 7 design principles. Now, I don't know how you're going to get asked them. You could just get asked in just a basic question, or you could get asked in underlying chemistry. Yeah, talk about, for example, underlying chemistry. Use your knowledge of chemistry. Talk about how you would start up a chemical industry, something like that. Yeah, but you need to know these 7 design principles. Now, the good thing is the majority of them, they're straightforward. Yeah, the first 3, straightforward, makes sense. Opportunities for recycling, energy requirements, marketability of byproducts, it all makes sense. Yeah, right. So let's carry on. Now, not only do we need to consider the 7 design principles, we need to consider the environment as well, okay? Because like I said, we're caring people. So chemists must also be considerate of the environment. Okay, so chemical companies must, and there's 3 points I want to make here. So chemical companies must, so the first one, must minimise waste by recycling where possible. Okay, and again, that makes sense. Yeah, you want to save the planet, save the environment. You minimise waste by recycling. Okay, so again, we spoke about the Haber process. So see Haber process. So that's all about recycling unreacted nitrogen and hydrogen. Okay, don't worry, next time I have a live lesson with you, I'll take you through a couple of examples. So minimise waste by recycling where possible. Next thing you want to do, and again, it's very obvious, it's nothing that doesn't make sense, avoid using or producing toxic chemicals. Yeah, that's a given. Of course, you don't want to be doing that. Yeah? And then the last one, if unavoidable, okay, so if you can't avoid this, if you're unable to, yeah, if you can't avoid producing waste, you want to produce waste that can decompose or biodegrade naturally. Okay, so if you're making plastics, you want to be making biodegradable plastics. Yeah, you don't want to be making plastics that are going to live on the planet forever. So that's your 3 considerations of the environment. Yeah, minimise waste by recycling where possible. Avoid using or producing toxic chemicals. And then finally, if unavoidable, you want to be producing waste that can decompose or biodegrade naturally. Okay? And very much like the design principles, you need to learn these. Okay? But again, the good thing is, they already make sense. There won't be one person sitting here being like, oh, I don't understand that. Why would we do that to help the environment? So they do make sense, but you do need to memorise it, and I appreciate it. It's quite a lot, but you do need to know it. Okay, now that's us for the chemical industry. I don't want to spend too long on that. I am going to put up some questions on our next live lesson. Okay, so don't worry about that. But what I want to do now is I want to go on to atom economy. Okay, atom economy. Now, this is a calculation, but it's an easy calculation. In fact, it's probably the easiest calculation we've done so far, or we will be doing. So, I'll give you a wee note on atom economy, and then we'll get straight into it. So, atom economy measures the percentage at which the total mass of starting materials successfully convert into a desired product. Okay, so atom economy measures the percentage at which the total mass of starting materials or reactants successfully convert into a desired product. Okay, so that's what we're after. We're after our desired product. Yeah, the product that we want. We don't want our byproduct, we want the product that we want, the whole reason that we got into chemical industry. Yeah, the product that we're making. Now that might not make sense just now, but it will when I start going over it. So if we just take a basic addition reaction, so we're going to take butene, okay, we can call it but-1-ene. We're adding bromine over the carbon-to-carbon double bond, and we're going to make that. Okay? Now, we're going to use our data booklet, and it's going to be page 5. It's the one that gives us all the GFMs. Yeah? Now, I'm going to do this in a different pen. We all know how to work out a GFM. Hydrogen is 1, we've got 8 of them, so that's 8. Carbon is 12, we've got 4 of them, so that is 48. So if we add that together, we've got 56 grams coming from the but-1-ene. Yeah, bromine, again we can use the data booklet for that. Bromine is 79.9. Okay, but we've got 2 of them, so we times that by 2, so that's 159.8 grams. So the mass of reactants equals 56, add 159.8, and that would be 215.8 grams. Okay, so that's the mass that we have with our reactants. Yeah, you're with me so far? Now, what we need to do is we do the exact same for the product. So the bromine, again, 2 Br2s, we already worked that out. is 159.8, hydrogen is 8, and 4 carbons is 48, and if we add that up, we're going to get 215.85 grams. Okay, so that's the product that we wanted to make. So the mass of desired product equals 215.8 grams. Okay, and hopefully you've noticed that it's the exact same as the mass of the reactants. Okay, so the mass of reactants we've put into this reaction is 215.8 grams, and the mass of our desired product, yeah, the product that we wanted, the mass of the desired product is 215.8 grams. So because we've got the same out, okay, let's make a wee note here. So since, oh, I'll go back to my black pen. So since the total mass of reactants and the mass of the desired product is the same, okay, it's got a very special name. We call this an atom economy of 100%. Okay. Now, go back to our definition of atom economy. It measures the percentage at which the total mass of the starting material successfully convert into a desired product. Now, looking at this reaction, the total mass of the starting materials, every single mass has been converted into a product. So because of that, we have an atom economy of 100%. Now, the cool thing about this is true for all reactions with only one product. Okay, and that's important. Let's highlight that. So this is true for all reactions with only one product. And that, it kind of makes sense, because if you're only getting one product, that means every single one of your reactants is going into making that one product. Yeah, there are no byproducts. So every single reaction that only has one product forming, you don't even need to calculate it out, because there's only one product. Boom, it's a 100% atom economy. Yeah. Now, it's not always going to be that easy. Yeah, it's higher chemistry. So you're not always going to be given a reaction with just one product. And in fact, the majority of reactions form more than one product. So we need to consider that. Yeah, so if a reaction has more than one product, okay, if a reaction has more than one product, then we use the following equation. Okay, now the good thing about this is that this equation, although I would expect you by the time your exam comes around May, I would expect you to know this off the top of your head, but obviously when you're in the exam conditions, you're nervous, you make mistakes, you forget, you have blanks. This is in the data booklet. Okay, so the percentage atom economy equals the mass of desired product. Okay, I'm going to put in brackets S because sometimes you're after more than one product, yeah? But the mass of the desired product divided by the total mass of reactants, and because it's a percentage, yeah, we need to times by 100. Okay, need to times by 100. Now, remember, we side note, this is in the data booklet. Okay, so although when the time comes, I expect you to memorise that off the top of your head, you do have a safety net. Yeah, and do memorise it, because you don't want to be spending time in an exam looking through the data booklet for the equation. Just know it off the top of your head. So, again, like I always say about calculations, the best thing to do is just to jump in, start doing examples after examples. So, number one, I'll give you a wee backstory. Right, I'm going to make a wee note here, okay, just at examples. I'll make a wee note here. Now, atom economy. I've always told you in Nat 5 that when you're doing calculations, never multiply the GFM by the number of moles in the equation. Okay, that's what the mole ratio is for. That's why we split our page into 3, to take care of the mole ratio. Okay, so this is the only calculation, where we multiply the GFM by number of moles of substance in the equation. Okay, you'll see what I mean. If you're not understanding what that means, don't worry. I will talk about it. So I'm just going to move number 1 down here so we've got a wee bit more space. But I'll come back to that. So the first example, the reaction of coal with steam. Yeah, steam is just H2O, but in the gaseous state. So the reaction of coal with steam produces hydrogen gas and carbon dioxide gas. Okay? The question, I want you to calculate the atom economy. Calculate the atom economy of hydrogen. Okay. Now this is the equation here. So coal, obviously it's just carbon, steam, water, and that is producing carbon dioxide and hydrogen. But you would be given a balanced equation, so in order to balance that, you put a 2 in front of the H2O and a 2 in front of the H2. So that is our equation there. Okay. Now, read the question. Okay, highlight. It wants to calculate the atom economy of hydrogen. So this here, this hydrogen, yeah, that is our desired product. Yeah, because the question is asking us to calculate the atom economy of hydrogen. Hydrogen must be our desired product. So what that means, see that carbon dioxide? Score it out. We don't need it. Yeah, we are solely focused on this beautiful molecule of hydrogen. Yeah, that's what we are focused on. Okay? So, what we need to do, I'm going to do this in red. Okay? So, we start with carbon, and you want to work out the GFM of every reactant. So, carbon is 12. Yeah? Now, oxygen, this is the important part. Watch this. So, oxygen, you should know, is 16. Hydrogen's 1, we've got 2 of them, so that's 2. So that's a total of 18. Yeah? Now watch what I'm about to do, because this is the important part. Now, this is the only calculation where we multiply the GFM by the number of moles of a substance. Now, the GFM of water is 18. The number of moles is 2. Okay? So what I want you to do, see this 2 here? I want you to bring it down, yeah, get an arrow, yeah, exactly like this, and then you're going to multiply like that, okay? So it's going to be 2 times 18, and that's going to be 36, okay? You have to multiply in atom economy, because we're considering every atom, because we've got 2 moles of water, we need to consider 4 H's and 2 oxygens. So you do it like this, yeah? So if I highlight the 12, highlight the 36. So the total mass of reactants, that's going to be 12 add 36, so it's 48 grams. Okay, that's our total mass of the reactants. Yeah. Now, like I said, carbon dioxide isn't our desired product, so forget about it. Who cares? We are focusing on the hydrogen. So hydrogen, we've got 2 of them. So that's H2, so that's 2. But remember, we've got 2 moles of it. So bring that 2 down. Yeah, bring that 2 down, and that's going to be 2 times 2. So that's going to be 4 grams. Okay, so yeah, that's going to be 4 grams. So our desired product, the mass of our desired product is 4 grams. Okay, now all we need to do, that's it by the way. That is the hardest part of the calculation. Yeah, Nat 5 could do that. So all we need to do now is the easy part. So we take our equation, the atom economy, yeah, so the one that we learned up here. So the atom economy, that is your mass of desired product divided by the total mass of reactants, and again, because it's a percentage, we need to times by 100. So let's plug in our numbers. So a mass of desired product is 4. The total mass of reactants is 48. So that's 4 divided by 48 times 100. And if I just do that in a calculator just now, 4 divided by 48 times 100, we are getting 8.3%. Okay, so 8.3%, that's quite a low atom economy. So that tells us we've got a lot of byproduct. Yeah, and it's carbon dioxide as well. That's a greenhouse gas. Okay, that's going to contribute to global warming. So this reaction to make hydrogen probably isn't the best reaction to use. Okay. Now, because we've got a low atom economy, percentage yield, we could get a high percentage yield. We could be getting a percentage yield of 80%. Just because we've got a low atom economy doesn't mean we're going to get a low percentage yield. Okay? So just remember that. Remember that. Now, I want you to make a wee note here. And this is a common mistake. It happens in percentage yield as well, and it blows my mind. But anyway, you can't have an atom economy greater than 100%. Okay, that's impossible. Okay, and same with percentage yield. You can't have a percentage yield greater than 100%, but for some reason, people give me answers greater than 100%. If you get an atom economy of 100%, okay, so if you do, chances are there's 2 mistakes you've made, or yeah, 1 of 2 mistakes. So if you do, chances are your GFMs are wrong. So you might have forgotten to multiply by the number of moles, or you might have said oxygen was 20 or something like that. So if you do, chances are your GFMs are wrong, or you have flipped the equation. Okay, and what I mean by that is that you put the mass of the desired product on the bottom and you put the total mass on the top. So if you're getting a percentage of over 100%, you need to rethink your answer. Okay, you've made a mistake and chances are that's one of the two mistakes you've made. Okay? Right, I'm going to do 2 more examples and then that'll be me. I feel that you'll be ready to do questions. So what I want you to do is I want you to calculate the atom economy. Well, sorry, we're going to do it together. So calculate the atom economy for hydrazine. Now you don't need to know hydrazine. Hydrazine is N2H4, and I believe it's used for rocket fuel. Okay, so but you don't need to know that. So calculate atom economy for hydrazine production. Okay, so I'm going to give you the equation. It's made by reacting 2 moles of ammonia, NH3, and we add it to NaOCl, and we are going to get N2H4 plus NaCl, sodium chloride, plus water. Okay? Now, because we're asked to calculate the atom economy of hydrazine, that there is our desired product. Yeah? Now remember what I said, circle your desired product, N2H4, and see the other products, score them out. Who cares? We're not interested in them for this calculation. Okay? So that N2H4 is our desired product. Now, let's work at the GFM. Start on the left. So H is 3. Nitrogen, if you use the data booklet, is 14. Okay, so that's a total of 17. Are we finished though? No, we're not. Remember, it's the only calculation where we multiply the GFM by the number of moles. So we bring that down, bring that 2 down. So that's 2 times 17, and we've got 34 grams. Okay, do the same for this one. So chlorine, 35.5. A lot of these you'll probably know off the top of your head because it's the ones that come up all the time. So 35.5, 16, 23, that adds up to 74.5 grams. Okay, so total mass of reactants. Okay, I'm going to do the reactants, I'll do it in yellow, so that's 34 grams, add 74.5 grams, so 34, add 74.5, we are going to get 108.5 grams. Okay, now we do the same for our desired product, so that's 4, nitrogen's 14, so 2 of them, that's 28. And that's going to be 32 grams. Yeah? So, the mass of our desired product is 32 grams. Okay, so that's the hardest part about this, is this bit. Yeah? This is a gift. 2 marks. This would be in the exam. Absolute gift. So all we need to do now is our equation. So atom economy equals mass of desired product divided by total mass of reactants. Because it's a percentage, times it by 100, so our desired product is 32, our total mass of reactants is 108.5, times that by 100, and if I just quickly put that in a calculator, 32 divided by 108.5 times 100, I am getting 29.49 Okay, so again, very much like the last one, this has a low atom economy, so got a low atom economy, yeah, but look at our byproducts, sodium chloride, water, yeah, they are environmentally friendly. Yeah, so this you could argue this might be a good reaction to make hydrazine, even though we've got a low atom economy. All it means is our the percentage of atoms from the reactants is quite low of our desired product, but our two products, yeah, they're not toxic. Yeah, salt and water, yeah, ideal. So low atom economy, but no toxic byproducts. So this is pretty good. It would depend on the percentage yield. Now, if we're getting a good percentage yield, ideal, perfect. But if our percentage yield is quite low, yeah, if we are supposed to be making 10 grams, but we're only making 2 grams, then it's going to be a bit of waste. That means these products are going to cost, yeah, these feedstocks are going to cost a lot of money to make just a wee bit of what we need. So you need to think about that. So the last one I want to do, this one won't take long. So it's going to be ethene, so C2H4, add water, so it's a hydration reaction, remember, yeah, adding water over a carbon-to-carbon double bond, hydration, and we are going to create an alcohol. That alcohol is ethanol, okay? So what we're going to do is calculate the atom economy of ethanol. Now, I don't even need to do a calculation here. And I want you to think why. Why don't I need to do a calculation here? Well, the reason I don't need to do a calculation here is because there's only one product. Yeah, and remember what we said at the start, the atom economy. If there's only one product, okay, only one product, therefore, we're going to get a 100% atom economy. Okay, there is absolutely no need to do a calculation. No need for a calculation. Okay, because we've got one product. That could save you a lot of time in a multiple choice question. Yeah? Now, I have actually realised just there that I haven't sort of explained, well, I have in a way, I've just not really gave you a note on it. A 100% atom economy. This is the last thing we're going to do. Okay, so a 100% atom economy. What we mean by that is that all reactant atoms end up in the desired product. Okay, that's all we mean by a 100% atom economy. All reactant atoms end up in the desired product. Yeah, and in the case of this one, we've got 2 carbons, that ends in the desired product, 2 carbons. We've got 4, 6 hydrogens, they end up 5, 6 hydrogens in the desired product. We've got 1 oxygen, that 1 oxygen ends up in the desired product. So all reactant atoms end up in the desired product. Okay? So, we've learned a lot today. Yeah, we've done the whole chemical industry, the 7 design principles, the 3 environmental factors that you need to think about, and we've also done, albeit an easy calculation, but we've also done an atom economy calculation. So it's up to you to go away, to consolidate and to sort of start memorising these 7 design principles, what a raw material is, what a feedstock is, the environmental factors, and I will, the next time we have a Teams meeting, I will go over some questions that would come up as part of the chemical industry. Okay, right, that's us, so thank you.